We're back to logarithms in lesson 3.2. So we're going to kind of go back to what we started this whole unit with. So we have the equations, and we need to understand that the equation y equals the log base b of x and b to the y equals x are equivalent. All right, so this is based off of kind of what we introduced chapter 3 with, understanding how to be able to change a log to an exponential and an exponential to a log equation. When evaluating logarithms, let's try that again. When evaluating logarithms, remember that a log is an exponent. Okay, remember the log is the exponent that you're looking for. It's the solution for the exponent. All right, log base a of x is the exponent to which a must be raised in order to obtain x. Remember we said if you see this, you say to what exponent do I raise a to get x? For instance, 2 must be raised to the third power to get 8, so the log base 2 of 8 would equal 3, because 2 to the third is 8. Use the definition of logarithmic functions to evaluate each logarithmic function at the indicated value of x. So all we're doing is taking the 32 and putting it in place of the x here, so we're going to evaluate f of 32. So we're going to say the log base 2 of 32. So here we're asking 2 to what power am I going to have to raise 2? To what exponent do I raise 2 to get 32? And our solution here would be 5. All right, since we've done some of these already, go ahead and pause the video, try out B, C, and D, and then come back and see me. All right, if you're back, hopefully you were able to do these 3. Over here, remember, anytime we take the log of 1, it doesn't matter what the base is, the log of 1 is always 0. We've talked about that property. Over here, the log base 4 of 2, we got 1/2. Again, remember, 4 to what power gives me 2? Well, 2 is the square root of 4, so we would have to take the square root of 4 to get 2. And remember, a square root is the same thing as raising it to the 1/2 power. X to the 1/2 is the same thing as the square root of x. And of course, that x can be any number. 4 to the 1/2 is the same thing as the square root of 4. Okay, so a quick reminder as far as that was concerned. And then down here, we have the log base 10 of 1 over 100. When the numerator is a 1, you look at the denominator. 10 to what power would give me 100? Well, that's 2. And then in order to get it to reciprocate or flip over and make it 1 over 100, we make it a -2, an exponent of -2. A logarithmic function with a base of 10, like the example D that we had up here, is called a common log, which we discussed in our intro to chapter 3. All right, we usually write a common log just with log. Remember, that's the one we don't put the base on. So if you see it just written log and there's no base written, it's assumed to be 10. All right, we're on to calculating some common logs or evaluating some common logs. So we're headed over to the calculator. And for each one of these on the calculator, you're going to be using this log button here, this guy right here. Okay, so remember we said we're only going to use that button when it's a common log, when it's a log with a base of 10. If it's not log base 10, you do not use that button. All right, so with that button, you're going to come through over here and do some evaluating for me. For this one, we have the log of 10. Which you can even do without a calculator. So it's log of 10, remember the base is 10, so we say to what exponent do I raise 10 to get 10? So our solution here would be 1. If we come down here though, we're looking at the log of 1/3. Okay, that one we will not be able to evaluate without the calculator because we're saying to what exponent do I raise 10 to get 1/3? So we're going to have to come over here to the calculator and we'll do log, oops, would help to turn it on, log of 1, not exponent, log of 1/3, and not cubed. There we go. Log of 1/3, -0.477. That's going to be our solution here. So equals -0.477. And again, I want 3 decimal places. You can round or you can truncate, either one. Okay, same thing with these two. Log of 2.5. and log of -2. Okay, so go through on those two real quick, type them into the calculator to see what you get. Hopefully your solution for this one was 0.398 or maybe 0.397 if you truncated. And then for the second one down here, when you try to type it into the calculator, what happened? Log of -2, we get an error. Why? It's a non-real answer. Another word for non-real? It's imaginary. There's no solution for this one, okay? So if you'll come back over here for me, this is an error. No solution. All right, so down here, notice the calculator displays an error message indicating a complex number when you evaluate log of -2. The reason for this is that there is no exponent that you can raise a base, a positive base, and we'll never have a negative base for these. There's no exponent that you can raise a positive base to and get a negative solution. All right, so anytime you try to evaluate the log of some negative number, it will always give you an error. That's very important once we start solving logarithmic equations, so please make sure that you're aware. You cannot take the log of a negative number. For logarithmic properties, we need to make sure that we're aware of, and now we're just kind of putting them all in one spot because we've talked about these already. The log, the first one is the log base A of 1. I don't care what the base is, what is the log of 1 always going to equal? 0, all the time, every single time, okay? The reason for that is because any base raised to the 0 power is 1. All right, so this is going to kind of be your reason. So we'll put in here a because. All right, next one. The log base A of A is always going to be 1. If these two numbers match, your solution will always be 1. The reason for that, because A to the first power will always give you A. So whatever number that is, if that's x and x, your solution is 1. If that's 10 and 10, your solution is 1. If that's a bazillion and 372, and that's a bazillion 372, your solution is still going to be 1. The next one, the log base A of A to the x power, whatever that exponent might be, is going to be that exponent. Okay, the reason for that, remember all of this right here equals 1. So then this little guy is all you have left. So that's why your solution ends up being 1. There's technically a mathematical solution. It would be A to the log base A of x is to equal x. So what I need you to remember with these two is anytime that these two numbers match, we know that this thing is basically going to cancel itself out and you're going to be left with x. Okay, I don't want you to mark through it now because you want it for your property. Same thing is true over here. A log of A, all of this cancels out and you're just left with your x. So again, those two properties are also very handy once we start solving logarithmic equations. Okay, the last one is if log base A of x equals the log base A of y, then, okay, what this is saying is that if I have a log with a base and then the argument here, log with the same base and a different argument here, then the arguments have to be equal to each other. X has to equal y. Now that only works when you have one log equal to one log. If you have more than one log on an equation, on one side of an equation, then you're going to have to do some other stuff first, and we'll get to that in a little bit. Okay, using those properties we just worked on, what is the log base 4 of 1? To what exponent do I raise 4 to get 1? For that matter, to what exponent do I raise any base and get a 1? Our solution again was 0 for that one. Okay, next one. The log base square root of 7 of square root of 7. Remember, if these two match, then your solution will always be 1. And then the third one, we said if these two match, then your solution is 1, but that 1 is multiplied by this little 20 that's here. So your solution here would be just 20. That's it. Okay, again, this is the one-to-one property. We discussed this a little bit back in lesson 3.1 as well. So using the one-to-one property, if you have a log equal to a log, and the bases are the same on those two logs, then the arguments have to be equal to each other. The arguments, again, are what you're taking the log of. So we have log base 3 of x equals log base 3 of 12. Therefore, x equals 12. Okay, because this log and this log basically cancel each other out. Same thing here. You have the log of 2x plus 1 equals the log of x. Question, what's the base? Okay, there's not one written. It's a common log. That's our base 10. But because it is the exact same base and we have the log of something equal to the log of something, the logs are going to cancel each other out and you're left with 2x plus 1 equals x, and we need to solve that for x now. Okay, so we have an x here and an x here. Combine your like terms. Probably easiest if I move this guy over and make it a negative x. So we have 1 equals negative x, which means that x would equal negative 1. All right, next problem. Log base 4 of this guy is equal to log base 4 of this guy. So the logs, again, cancel each other out, and we have x squared minus 6 equals 10. Okay, so we're solving this for x, get x squared by itself. So x squared would equal, we're going to add that 6 to the other side, so we get 16. And x would equal, we're going to take the square root of each, so the square root of 16 is 4, but I have to put that plus minus in the front to get our final answer. Okay, because these are equations, you can always go back and check them. All right, graphing a logarithmic function. To sketch the graph of y equals log base a of x, you can use the fact that the graphs of the inverse functions are reflections of each other in the line y equals x. That goes back to our pre-3.2 lesson that we discussed. Okay, if I know that 2 to the x is the inverse of the log base 2 of x, then I can graph this guy because it'll be way easier to graph, and then switch the x and the y values to graph this guy. All right, so we're going to start with x value, and we're going to start with f of x, which is 2x, 2 to the x. We're going to pick a few x values and plug those values in up here and get some y values, and then we'll plot those points. We're going to have a table of values. So we'll do -1, 0, 1, and 2. We'll give those a shot for right now. So if I plug -1 in up here, 2 to the negative first. Again, that -1 is an exponent. Think 2 to the first is 1, but because it's negative, I need to reciprocate it. Sorry, 2 to the first is 2, and because it's negative, I need to reciprocate it. So it becomes 1/2. If I plug in a 0, 2 to the 0 power, anything to the 0 power is 1. Plug in a 1, 2 to the first is 2. And plug in a 2, 2 to the second is 4. So I've now come up with 4 points that I can plot. So we have -1 and 1/2. We have 0, 1. We have 1, 2, and we have 2, 4. So this guy right here is the exponential function f of x equals 2 to the x. Now, knowing that this is the inverse of this, to find these values, all I really need to do is to switch the x and the y of these values. So that would mean these guys right here. So my new x and y values are just going to be the the flipped-flop versions of the f of x function. So we had -1, 1/2 as an ordered pair, so now we're going to have 1/2, -1. We had 0, 1, so now we're going to have 1, 0. 1, 2 becomes 2, 1, and 2, 4 becomes 4, 2. Okay, now that we have those points, those ordered pairs, we can plot them on the graph over here. So when x is 1/2, y is -1. When x is 1, y is 0. Then we have 2, 1 here, and 4, 2 here. And this one follows along the y-axis, and then will come out like that. So again, it needs to be a reflection over that line y equals x, which is your parent function, parent linear function coming through the middle like this. And all we did is take these four points and reflect them over that line to get these guys. And this is my g of x equals log base 2 of x function. Okay, so again, the easiest way if you have to graph a log by hand is probably to graph its exponential function or figure out its exponential inverse function and then flip the x and the y values like we did here. But that also illustrates to those two are inverses. All right, sketching the graph of the common log function, log base 10 of x, and we need to identify the vertical asymptote. The vertical asymptote is always going to end up being the y-axis, so x equals 0, unless we have had a horizontal shift. So if we've shifted one way or another. If we shift one way or another, then obviously my asymptote is going to move as well. Okay, but if we're making the graph, it's going to cross at, for this graph right here, f of x equals the log of x, it's going to cross at 0, 1, or sorry, 1, 0. It's going to follow the asymptote, the vertical asymptote here, and then it's going to shoot up like that direction. All right. Logarithmic functions are always going to have this general shape. Then we can always reflect them. We can stretch, compress. We can do all the transformations we've done in the past with these functions. So again, right here, the y-axis is going to be your vertical asymptote until we do shifts. So down here, shifting the graph of a logarithmic function. Hypothesize what each logarithmic function does compared to the parent. So again, going back to transformations, we have a -1. It's grouped in there with the x. So is that an a, a b, an h, or a k? That should be an h value. So this guy is actually going to be shifted to the right by 1, which means that I'm going to take that vertical asymptote that was on the y-axis and I'm going to move it to the right 1, and then the graph will follow. This one over here, this one, the 2 is not grouped with the x. We could actually rewrite it as the log of x plus 2, but usually they put the 2 in front so they don't have to worry about the parentheses and all that good stuff here. So the 2 would become a k. So that's going to be my vertical shift. We're going to go shift up 2. Okay, if I'm shifting up and down along this asymptote right here, the asymptote won't move if I'm shifting up or down. I'm basically just moving the points up or down along this line. We had briefly discussed in our introduction in chapter 3 the natural log function. In 3.1 we had talked about e, and if you'll remember, e is approximately equal to 2.72. Remember, it's an irrational number. It's kind of like pi because e represents a particular number that's irrational. All right, so e to the x is a one-to-one function, which means its inverse is also going to be a function. The inverse function is called the natural log. And it's noted by the special symbol ln, okay, read as natural log. Not sure I had anything else special that I needed to put in there. Note that the natural logarithm is written without a base. The base is understood to be e. So there'll be 2 times that you will have a logarithm that does not have a base on it. One of those times is when you just have log of some number like this. The base is understood to be 10, and we call that a common log. You can also have a log written like this, and the base here is understood to be e, and that's our natural log. Again, those, remember, are our 2 special logarithms. Right, if we're evaluating natural logs, there is a button, just like there is for the common log. Again, they have their special buttons. So if I'm evaluating a natural log is going to be using this button right here. Common log, this button, natural log, this button. And again, the base is always going to be e there. So evaluating the natural log function, use the calculator to evaluate the function given by g of x equals ln of x. So we're going to evaluate, in this case, g of 2, which means I'm going to do the natural log of 2, and we come over to the calculator and we type in natural log of 2 and we get our decimal 0.693. And again, remember, I'm wanting you to round to 3 decimal places if it's necessary for us to round. Okay, go ahead and use the calculator. You're going to plug all of these in the exact same way. See if you can get the solutions that I'll give you when you come back. If you're back, hopefully you were able to get for B a negative 1.204. C again gave us an error, just like we had before with a regular log. And then down here with D, we have 0.881. So again, notice the natural log of negative 1 displays an error because natural logs, just like regular logs, only are good with positive x values, positive input values, positive arguments, however you want to call it. Okay, all of the properties that we just got through covering with regular logs also apply to natural logs. We're going to practice that a little bit on this next page. So, same properties that we have here. So we could actually rewrite this. We have the natural log. Again, the base is understood to be e, we just don't write it. And I'm going to reciprocate this guy. I'm going to flip it over. So instead of it being e to the positive first and it's down here, if I reciprocate it, it becomes e to the negative first. Now remember, the base down here is already e because that's understood for every natural log. Now there was a property that said when these two guys match, this whole thing equals 1 and basically goes away because 1 times the exponent would mean negative 1. All right, let's give the next one a shot. We have e to the natural log of 5. In this case, this is like I was telling you guys before, we have e to the natural log. Again, what's the base down here? We have base e of 5. So again, that's that 1 to 1. These guys are going to cancel out. They're all going to equal 1. And then the 1 times 5 gives me 5. Okay, our next one, don't worry about the divided by 3 right now. Let's take a look only at the natural log of 1. What is the natural log of 1? So we're saying to what exponent do I raise e to get a 1? And the answer would be 0. Natural log of 1, they're all going to equal 0. So this guy equals 0. 0 divided by 3 is 0. So our final solution here would have to be 0. And the last one down here, we have a natural log of e. So we have 2 times the natural log of e. Again, the base down here that's not written is an e. These guys, remember, will all equal 1 because the exponent here is a 1. So all of this is 1 times 1. All that cancels, and our solution would be 1 times 2, which is 2. Okay, finding the domains of logarithmic functions. This could work for regular logs or natural logs or common logs. I would suggest that you are graphing these. To me, that's the most efficient way for you to be able to find the domain. And again, the domain, remember, domain is what x values can the graph either use or not use. Most of the time it's easier to say what it can't use. So the first one, we're doing the natural log of x minus 2. So I'm going to come to y equals and I'll type in natural log of x minus 2. I'm going to clear out this other guy. Oops, I just cleared out the wrong one. We'll just do it down here, natural log of x minus 2. And once we graph it, if you notice, I'm not using any x values over here. Okay, so the very first x value, if I'm moving from left to right, the very first x value I end up using is actually right here. If I press trace, it would be at 2. Okay, and I don't even get to use the 2, but I could use 2.001. So we basically say anything, and notice the graph doesn't even look like it comes down here. That's because there's an asymptote here, remember? We kind of talked about that. And because of the pixels on the calculator, you actually can't really even see it. Okay, so won't be able to see that graph. But it does continue to go down, and it goes down forever and ever, amen. Okay, so as far as the domain is concerned, it's going to be all the x values from 2 to infinity. Remember, we could not use the 2, so it has to be a parenthesis, and then infinity, it's always a parenthesis. So the domain for this guy would be from 2 to infinity. And we call that exclusive because it do not include these values. If we try the next one, now we have the natural log of 2 minus x. And when we graph this guy, notice now, as we move from left to right, we're using all these values, and it's going to keep going this way. So we're coming from negative infinity all the way up to, and again, this is going to be a 2. But if I type in 2, I don't get a y value because it can't ever actually equal 2, so it's going to be everything all the way up to 2. So our domain here is going to be from negative infinity, again, always a parenthesis on the infinity, and we're going to go all the way up to 2, but we can't equal 2, so we have to use a parenthesis again. Our last one, the natural log of x squared. So if we do the natural log of x squared, right, basically what it's doing is it's going to be able to use all negative x values and all positive x values, and it's turning all of those into y values, so it actually will work for all x values. So if I come from here, I'm coming from negative infinity all the way down. Let's check that at 0. So we're going to trace when x is 0. Uh-oh. We get no value here. So when x is 0, y cannot be anything. So I can use all these x values. I can use all these x values, but I cannot use that x value. So the only x value I can't use is 0. So the domain, in this case, we're going to say, you can write this 2 ways. So in interval notation, it would be from negative infinity to 0, union 0 to infinity. That's your interval notation. Again, the union tells me these two have to go together, and because I used parentheses for both of these, it tells me that the 0 is not included. The other way you could write it, as far as set notation, is the set of all real numbers except x equals 0. Okay, 2 different ways of writing the same thing. So either way. Last one for the application problem. So it says students are participating in a psychology experiment. Students, I think it's supposed to say who are participating in a psychology experiment, attended several lectures on a subject and were given an exam. Every month for a year after the exam, the students were retested to see how much of the material they remembered. The average scores for the group are given by the human memory model, and that's this guy right here. Notice it's a natural log model. And t is between 0 and 12, which are the months. So use what you know about log functions to predict the shape of the graph. Confirm with your calculator. Remember, all natural log functions are going to have that kind of shape. All log functions are going to have that kind of shape. And if we confirm with the calculator over here, we have 75 minus 6 times the natural log of x plus 1. Okay. If we don't see anything, the reason why is because we've been shifted. So we're going to zoom out a good bit here, because that 75 actually shifted me up a good bit. Still not enough, is it? Okay, so for my window, let's go 0 to 12 because that was my months. And then up here, let's go y minimum of 0, but a y maximum of 100. And now let's see what happens. Uh-oh! My prediction over here wasn't the same. Why not? Just like with our other transformations, that sign in front of my natural log was negative. What's that going to do to my graph? That's going to reflect it over the x-axis. Now, does it make sense that if you took a test now, and then you took the exact same test a month from now but didn't study or anything, doesn't it make sense your score would probably go down? Okay, just wondering. All right, what was the average score on the exam when t equals 0? In other words, the very first time they took the exam. So we're going to press trace. We're going to type in a t equals 0 or an x equals 0, and obviously it would be 75 as your average starting score. What was the average score at the end of 2 months and the average score at the end of 6 months? So again, we'll come back over here. We'll trace. At 2 months, our average score was 68.4. And at 6 months, our average score was 63.32. Okay, so we have for this one 63.32, and this one was 64 point something, but I don't exactly remember. What was it? Let's trace it at 2. Oh, sorry, 68.4. I got a 4 in there somewhere. 68.4. Sorry, I'm not doing my 3 decimal places. It's too hard to try to transfer all that back and forth. Determine the time. So if it says determine the time, I'm trying to solve for t. What is t? Okay, so now I don't know t. We're looking for when the average score is 60. So if you'll come back over here, we're now looking for when is the y value going to be 60. So our best bet is either to continue scrolling, maybe take a guess. I would say 10. Whoops. Maybe 10 months. Ooh, that's pretty close. So let's see, maybe at 11 months. Looks like we're really close, around 11 months. So at approximately 11 months. So determine the time in months. At 11 months, the average score should be around 60. Okay, just a different example of how this actually could be used in being able to graph data, gather data, apply data.